in previous lectures on rigid body, what we have seen is that if you have a rigid body rotating about an axis, let us take our origin here, then the angular velocity omega is a vector quantity. And any vector which is attached with the body or rotates about the axis. Because this vector is rotating, there is a change in the vector. Here I have taken vector r, so dr over dt because of this rotation is omega cross r. We have fixed the convention of direction of omega, and this is purely by rotation. The direction of omega is such that if the body is rotating along the fingers, the thumb gives the direction of omega. This equation is true for any vector, not just r. So, in general, any vector that is rotating about omega, its rate of change is given by omega cross a, and I am writing rotating here to indicate that this is purely due to rotation. Using this, therefore, when a body rotates with angular speed, angular velocity omega, this is the axis, this is the origin. You see, I am specifying origin all the time because we always take angular momentum or any quantity with respect to the origin. Then the angular momentum L, which is defined as summation over all the points in the body which are moving, mi ri cross vi is written as summation I mi ri cross vi is dri dt, and this is purely by rotation, this quantity, and this we worked out comes out to be I xx omega x plus I xy omega y plus I xz omega z in I direction plus I yx omega x plus I yy omega y plus I yz omega z in j direction, y direction, and I zx omega x plus I zy omega y plus I zz omega z in the k direction, where x, y and z directions are given, x, y, and this could be your z direction. And therefore, in general, to calculate the angular momentum, I need all these quantities. The diagonal elements Ixx, Iyy and Izz are the moments of inertia about the x-axis, about the y-axis, and about the z-axis respectively, and these quantities, the off diagonal elements, are the products of inertia. So, in general, it is quite a quantity to calculate. However, what we learned is that there is a simplification, and that is about any point in a rigid body there is a set of x, y, z axes. There is one set which is in one particular direction, so that all off diagonal elements Ixy, Iyx, Ixz, Izx and Iyz, Izy, these anyway are equal, but they are all equal to 0, so that the angular momentum is now quite simple. And let me change, instead of x I am going to call it axis 1, omega 1, 1 denotes x direction, so omega 1 is a component of omega in x direction, I plus I2 omega 2 j plus I3 omega 3 k. So the expression really gets simplified. The only catch now is that these I, j and k unit vectors are along the principal axis or principal axes 3 x, y, z of the body. Now principal axes are going to have a fixed orientation with respect to the body, and therefore these axes are attached with the body. As the body rotates, these axes also rotate. So that is the catch. So we have to take care of that somehow or the other when we develop our dynamics. But this is quite a simplification, that for a given body, suppose these are the principal axes x, y, z, then the angular momentum is going to be given as I1 omega 1, and for now let me now change this to 1, 2 and 3 in this direction, plus I2 omega 2 in y direction, plus I3 omega 3 in k direction. This is diagonal. Notice, however, if I1, I2 and I3, the three moments of inertia are not equal, then L is not parallel to omega. So if suppose this is omega, so that it has components in x, y and z directions, 1, 10, 2 and 3 directions, this could be L. Even if we take omega to be a constant, and even if omega 1, omega 2 and omega 3, that is the components of omega along the principal axis omega 1, omega 2 and omega 3 are constant, L is going to change, because L rotates. About omega. Why does it do so? Because L1 equals I1 omega 1, L2 equals I2 omega 2 and L3 equals I3 omega 3. All three are constant because of omega 1, omega 2 and omega 3 remaining constant, but the principal axes are themselves rotating. So these components, although they are fixed, they are rotating, and therefore L itself rotates about omega. So what we see is, in the case of x, y, z, principal axis omega and L not being parallel to omega, L could be I1 omega 1 I plus I2 omega 2 j plus I3 omega 3 k. All these numbers may remain unchanged, but L is going to rotate about omega, because the principal set of axes being attached to the body are rotating about omega, and the rate of change because of this rotation is going to be omega cross L. We will see a few examples of this kind later in the lecture. But before that, let me also for completeness show you what the kinetic energy of a rigid body is when it is rotating. So, let us see, the kinetic energy by definition is equal to summation mi vi dot vi, which I can write as 1/2 summation over I mi vi dot omega cross Ri. This is a dot product of a vector with a cross product. So, I can use the permutation formula and write this as 1/2 summation I omega cross Ri cross Vi, and Mi is always there. Since this omega is constant, summation Mi Ri cross Vi is L. This comes out to be 1/2 omega dot L. So, the kinetic energy of a rotating body is equal to 1/2 summation omega dot Ri cross Vi. I am deliberately writing Mi on this side, and this summed over is L, which is 1/2 omega dot L, and using L equal to, in the principal axis notation, omega 1 I1 omega 1 I plus I2 omega 2 j plus I3 omega 3 j k. This comes out to be 1/2 I1 omega 1 square plus 1/2 I2 omega 2 square plus 1/2 I3 omega 3 square. So, you see, if I work with the principal axis of the rotating body, my expressions, it becomes simple. Added complication is that now the principal axis itself is rotating with the body. So, we have to now look at how to handle this.